Let's say I have a requirement of 32-bit register. Okay. Now, so there are two ways to do this. One is basically 32 one bit registers, one bit registers. Okay, that is one. And second is you can also choose, say, SRAM. Okay, that is basically a memory which will save your data, say 8 cross 4. Okay, so that is one option. Or say second is SRAM 16 cross 2, and then again, or SRAM 4 cross 8. Okay, so these are all different configurations how it is going to be. Now if you guys ask me, say SRAM 2 cross 16. Now let me just show you. So why, on what basis? So if you look at, right, like kind of, what is the difference between these two? So end of the day they would be storing the 32-bit value. Okay, both of them will store the 32-bit value, and all this four will store the 32-bit value. Okay, now when I said this, right, so it is, we actually get this macros as a, memories as a macro. Okay, so let me just pull up my, the environment. I will show you guys. Okay, so meanwhile, so you have got a size, so individual, register. Say this is one bit, say kind of SDFF. I also asked you guys what is the difference between DFF and SDFF, right? Or say DFF. Okay, now if you guys see this particular design, now what is this cell? This is basically a cell. You can actually, go here and check ref underscore name. Okay, you will see something that, okay, now I just selected. See, if you look at here, these are all the cells which are all, say this is a big. Okay, now say this is another type. It is kind of, different size. Now say this is a different size. Now this is a different size. Now, so you can actually ask your RTL guys to pick any of this which could fit in your area. So now if you look at here, the first one is, the bigger one is 128 by 16, and then you have got 64 by 32, and 32 by 4, and 64 by 8. So your memories will be something like this always. Okay, now, so let's try to understand that, what is the area of your SDFF. It is like kind of one particular thing. Okay, so let's do this. So we have this cell. Okay, we have this cell. So 32 into 4, what is it going to be? So it is going to be 128 bit. Okay, so it is going to be 128 bit storage. Okay, now 128 bit storage. Now what is that I am going to do is 32 by 4. Now let me just take the, okay, so this is going to be 32 by 4. Okay, that's 128 bit. Now, so I want to check the area of this particular thing. Okay, so area is if you look at here 3606 or say 3607. So 3607. So this particular macro is having an area of 3607. Okay. Now what I wanted to look at now is I want to now get SDFF area. Let's just go and zoom and pick one of the SDFF. Okay. Say this flip flop. Okay. Now this area is going to be 9.15. Okay, 9.15. So 9.15 into, you can like kind of what do you call uh, that 128 bit. Okay, say something like that. Okay, now let's go and look at get attribute, say get selection. Okay, and then just say area. Now this is going to be the case. Now if you guys look at this is a dual port RAM. Okay, so you guys have to understand that read and write can happen in parallel. Okay, so the area of that, it is actually, we have just looked at 360607. Now this is going to be y expression. So 128 into 2 into 9.15. So now in this case you are actually kind of getting benefit when you use individual registers. Okay, but remember I have seen, you know uh, memories will give you lesser area, they consume lesser area compared to your flip-flops. So this is how I actually calculate it. So when I have to calculate whether memory is going to help me in the reducing area, or flip-flop is going to help me in terms of area, or there may be a different memory type in this itself. So here two, dual port RAM, right? So the read and write can happen at the same time. Okay, now what is this meaning is, so you can write on one bit in parallel, and you can also read from the another bit also. So that will actually improve your performance. So that's what it is. So your homework, what is meant by single port memory, single port memory and dual port memory. That's your homework for you. Okay, single port memory and dual port memory. Okay, all right. Now the way I calculated area, so when you get into industry and when you have to make some calculations, or identify, okay, so will memory makes area efficient or your flops makes area efficient, this is how we actually calculate it. But I'm telling you, this and all I have done in my whole career for only one project out of 40 plus tapeouts. Okay, that was because it was too much area critical. That is why I had to do that. And also remember, sometimes what we do is, say you have this bigger memory. Okay, now 64 into 32, what is it going to be? So 64 into 32, 64 into 32, now 2048 bit. Okay, now so you can also collapse this bigger one into smaller. So you choose this. Now this is what, 32 into 4, right? So EXPR, so 32 into 4. So it is going to be 128. Now, if you have to replace this bigger memory with a smaller one, it may be multiple reasons. So you can actually, split the bigger memory into smaller ones. Say, end of the day, how you are actually taking care of it. So it's a simple, I'm sure everyone would have gone through something called microprocessor. So how your memory that gets allocated, and what bits are kind of how the memory mapping actually happens and all of that. So now this is the requirement. So 2048 is your requirement, but you can actually use this memory. So now how many such memories you need? So expr 2048 divided by 128. Now if you look at this, one memory can hold how many bits data? 2048. Now what is the area? Okay, so this memory is actually having this particular thing. Now your small memories area is basically, so 3606. Now how many such small memories you need? So you need 16 memories. So 16 into this number, it will be big. So if you look at, there are, you have an option of using one big memory, okay, or the same thing you can also implement it using smaller memories like this. It need more memories, okay, it might need more memories, okay. So such things, 16 is something that you need. Now if I ask you, is using some bigger memory is better or using smaller memory is better in terms of area?
Bigger memory is better.
Which one?
Bigger memory is better.
Okay. So so that's what I was telling you guys. So it is, you have to understand what is your requirements. And let me tell you, whatever that I'm teaching, we have not started PD yet. So don't be, scared, or don't be kind of, worried. These are all some basic things that any electronics engineer should know. Say, because you are the one who's actually optimizing the area of a chip. Okay. And I'm telling you, maybe out of 20 projects, you will have to go this level in one project. Okay, as I told in my last, 40 plus tapeouts, I have done such things and broken this bigger memory into smaller ones, or split this into smaller ones, or grouped many smaller ones into a bigger one. So there are many things that I have done. That was only for one project. So don't be, don't get scared that, okay, no, these are all too much, I won't understand. These are all not your regular work. These are all your lead work, or your manager will have to do it. But you knowing them is an added advantage for you. Okay, as simple as that. Okay, all right. So to answer your question, the way, it depends what is your flop that is going to be used. Okay, that is one. And the second is, you have to pick the right memory, and even that memory, you can actually, there are two ways. Either you can use it and achieve, using a small memories, and you can achieve the same thing, or you can actually pick the bigger memory and achieve the same thing. Okay, a simple thing, right? So this is your memory. Okay, I'm sure everyone knows what is Snapdragon processor and all of that, right? Okay, Snapdragon, Snapdragon processor list. Let me just share this particular screen. So, so Snapdragon processors. Okay, so 8 series platform. Now, I want you guys to understand. So L1 cache. So you guys might have heard about something called L1 memory, L2 memory, L3 memory, and etc. Okay, so okay, if you see here what it says, so 4 KB memory, okay, and then there is a 16 KB memory, and then there is a 2 MB memory. So this is, you might ask me Kumar, why do we need these memories? So now, if you look at your design, may have these kind of memories or macros, which could actually store the value, and they can be used for operations. Okay, they can be used for operations. Okay, so that is why I say these memories. Pretty much each and every block, you will have these kind of memories. Okay, is that clear? Did I answer you guys? I've shown you how to calculate it and how do you decide which is going to work and etc. Okay. Okay. Now the next question that someone was asking, um, what was the other question? I think I forgot. What was the next question?
Yes, and the thing DMX circuit, that circuits and all where we
Ah,
use in that.
okay, got it.
Mm.
So you are asking me like kind of when. So for a PD engineer, the state machines and all these matters are not right. Okay, so let me explain you. Okay, now, say as discussed in the last class. Okay, let me just pull up the state diagrams. So now, if you look at here, end of the day. Now, say this is a state machine. Assume this is kind of using a state machine. I am going to design a counter. Okay, so this is a kind of state diagram, and then I would be coming up with the circuit. Correct. Now the question here is, end of the day, the circuit translated into what? The circuit gets translated into what? So counter meaning what exactly? Counter would be what? What is that circuit counter? See counters. What is it going to contain?
Counts the number of clock pulses.
I'm not asking that. Okay, let me just pull this. Okay, you see here. So this is one counter. Got it? This is one of the counter design. Now, say there is another counter. Got it? Agree? Now, say there is another something like counter. Okay. Now, you see here, this is also counter and etc. Got it? Now, end of the day, whatever that you see here, they are all going to be divided as a what? This is your input, and this is going to be your out, and there may be some in to out logic also. Okay, and things like that. Okay, now if you look at this particular circuit, any digital circuit that you take, they fall one of this category. What is this? Into reg. So this is into register. So input to your register, so through a combinational logic. So that is a one type of path, into reg. And then you have something like kind of reg to reg. Okay, and then you have something like kind of reg to out. Okay, and then what is it this going to be?
Into out.
So in to out. Okay, so these are four different categories of paths that we divided. Okay, now when I say this, it doesn't matter what circuit it is in your case. whatever circuit that you have, this can be, you know what, now you look at here, this and this. So this is Q, this is a kind of combo, and it is going to your say D. So this becomes a reg to reg. Okay, now here there is something here, and then it is going to this. So this is basically into reg. Now what about this guy? This guy is again kind of, you can say, reg to reg. So this reg to reg. So you will have design that is kind of divided into four different paths. That is what we look at it. So you don't need to worry about what is a state machine or state diagrams and all of that. That is not what we as a PD engineer would do. We would actually go and you know uh, look at any design functionality. It can be anything, and as a PD engineer we won't know the functionality because they just tell that okay, it is just a transceiver or transcoder or set-top box chip or just a CPU and things like that. But if you ask me whether do I know the logic in between those two, the rich to rich, definitely I won't be knowing. I can give you a simple quick example here. Okay. Okay, now say simply, if I want to, highlight how you can look at your design, right? Now you look at here. Okay, I'm just showing you a sample design that what we have, and you actually now go through this. So what is it you guys see here? What is this? What is this? And what is this? So let's just zoom it, and then you can actually check. Okay, now what is this cell? You guys can see here. What is this? This is basically SDFF. It is basically a register. Okay, what is the category that it is falling? The data is launching from your register. Okay, which is this. Assuming, see, data is getting launched from here. This output goes through a lot of combinational logic. What is this cell? Seems like OR gate, and then seems like a AND gate, and then inverter, and this is going to be OR, OA cell and all that. Now let me just pull this side by like this. It is actually a full adder. Okay, and then you have some three input and then you have got a four cross one mux, then again full adder. So your digital whatever that you have read, that is all the same thing that you will see now. See, it's just going through all the combinational logic, and then it is ending at where another register. Now what is this path we call it? Any idea what is this path that we call it?
Reg.
Exactly, so it is a reg to
Reg.
reg. Okay, so now this is one category of it. So because I just clicked only on reg to reg path, so that is why it is kind of reg to reg is happening. So the same way you can actually divide any input port to this first register. It is going to be kind of into reg, and then reg to reg. The data is launched from a register, and if that gets captured by another register, okay, it is called reg to reg. And this one, register to output. So it is basically from this register, it is going out of your block. and then there may be some blocks. Okay, so your homework. What is this out paths? Into out paths. Why do we need them in the design? So what is this into out paths, and why do we need them in the design?
Feedback is that.
No, it is not feedback and all. It is, so there are terms. So you try to figure it out. Okay. So I can just give you a quick simple thing. Say for example, if this is your design, big design. Now this design is divided into smaller things. Okay. Say something like this. Okay. Say you have a design like this. Okay. Now assume this is the block. So from this block, it has to go here. So it is talking from one block to another block. Now, how this can actually go inside? How will you implement this? What is this called? So this is what I want you guys to go through. This is what I want you guys to go through. There is a term for it, so that is why we say into rich, into out also is a important thing. But what is your first priority? The first priority is ridge to ridge, but second priorities are your interface paths that are basically into ridge, ridge to out, and then into out. Because ridge to ridge is already your high priority. Okay. Um, so to answer your question, when you have a counter, or or when you have a state machine, or any design that is having a state machines, obviously almost all the designs will have state diagrams, and they will try to solve it with the help of the tools, and then all that. So the only thing that you need to understand is this is going to be kind of ridge to ridge paths, which is your first priority, and your into ridge, ridge to out, and into out, all that are basically second priority. Okay, so any question here? Is that clear?
Clear, sir.
Okay, I'll just give you guys one more minute. If you have any question on the digital side, I'll try to help you out. If not, then we will move to the CMOS part. Okay, no questions? All right.